Today I want to change the core data structure of my compiler. Currently, in very broad strokes, the system works as follows. The files that are passed into the compiler are tokenized, preprocessed into an array of tokens, and then split into global declarations. Each of these global declarations is then thrown into the parser. The parser then generates an abstract syntax tree, or AST for short. For data declarations, we then invoke a function called evaluate static initializer that walks down the AST to try to bake down the initializer to just a set of bytes. Plus, if the initializer also references another global declaration, we also have to emit a patch to that global declaration. For functions, we also walk down the abstract syntax tree and just linearly emit x64 instructions. Plus, again, potentially patches to other global declarations. Finally, we generate an executable in memory. The data declarations are thrown into the .data section and the functions into a text section. And now that we know where everything is located inside of the executable, we can apply the patches we emitted and write the file out to disk. But most other compilers have at least one more step. Namely, instead of just producing x64 straight from the AST, they first produce some sort of intermediate representation, or IR. Some compilers even have multiple IRs. For example, the ZIG compiler first produces ZIR, and then it analyzes that ZIR to produce AIR. The Rust compiler even has 3 intermediate representations for whatever reason: her, the, and mer. And both of them probably in the end also produce LLVM IR because they use LLVM for optimizations. So what an intermediate representation really is sort of vague. For example, one could argue that the AST is some sort of intermediate representation. After all, it is not the source code, the initial representation, nor the end result, like the executable that we produce in the end. But usually what compiler people mean when we talk about an intermediate representation is something that looks a lot more similar to machine code than to an AST. So instead of having these free-flowing nodes, there's sort of the concept of a sequence of instructions. One of the simplest common intermediate representations is the so-called 3-axis code representation, where each instruction has 3 operands, 2 source operands and 1 destination operand. In this example, you can see how this kind of IR might conceptually look. On the left here, we have a somewhat complicated formula, calculating a solution to a quadratic equation. And then we can split this formula into its sub-expressions and sort them by the precedence of their operation. For each of the sub-expressions, we then introduce an intermediate variable. Later sub-expressions can then refer to earlier sub-expressions by these variables. And in some sense, you can still see the abstract syntax tree in this representation. A sub-expression, or what we could call an IR instruction, refers by temporary result to a previous operation. So in some sense, the difference is really that we sorted the nodes in execution order. Put a pin in that will become important later on. Another type of intermediate representation is a stack-based one, where the operands are implicit. So instead of having these instructions that name their argument, there is an implicit stack. Primary expressions, like for example integers or identifiers, push the corresponding value to the stack. And then operations, for example an add, would pop both of the arguments from the stack and then push the result. And this is the kind of IR I want to replace my AST with. Why do I want to do this? Well, because this function, parser ast push, started to show up in profiles. Literally all this function does is to linearly allocate an AST node, which essentially should amount to incrementing a pointer, and then initialize the common members of the AST node. So likely where the slowdown is coming from is memory pressure. And by reducing the amount of memory that is being allocated and then written, we should be able to improve compilation speed substantially. Well, how do we get started? I am usually not the kind of programmer who thinks a lot. I am usually the type of programmer who simply presses buttons until it works. because after all, thinking is for nerds. But for these kind of massive refactors, I think it's important to have some sort of strategy. Some sort of strategy that allows you to make incremental progress while keeping the whole system still running and operating. And this is where the thing about ordering AST node becomes important. The first step will be to ensure that the AST nodes are allocated in execution order. So let's talk a little bit about allocations. Currently, the way allocations work in my compiler is that every thread has two arenas. Arenas are simply linear allocators, so essentially just a pointer into a big reserved region of memory that gets incrementally committed. If you don't know what arenas are and why they are great, there are a bunch of videos online about them. Anyway, one of these arenas is for permanent memory, so everything you allocate into this arena will not and cannot be freed. And the other one is for scratch memory and gets freed at the end of every task. So for example, passing a function, passing a declaration, or emitting code or whatever. Obviously, the AST nodes are needed throughout the program, and thus they are currently allocated in the permanent arena. But that means that currently there may be random allocations between AST nodes. To avoid this, the first step is to introduce a new arena to every thread. Let's call it the AST arena. And this arena will only hold AST nodes. For starters, I will only use this new system for expressions. Therefore, I split the parser AST push routine into either push expression or push AST. This is maybe a little bit confusing because push AST is now used for statements and does not use the AST arena, whereas push expression does. But whatever, we can fix up naming later. Now, every call site that previously used parser AST push is complaining, and we can choose to either use push AST or push expression. Here, when doing these large sort of refactors, I think it's important not to get bogged down with the details. If I don't know what to do, instead of thinking long and hard about it, I simply put a tag on it telling future me like, hey man, I didn't know what to do here, this thing may be wrong. Here in the end, I choose the IR refactor tag. After making this change, the only real difference now is that the AST nodes are all sequentially allocated in the AST arena. Functionally, this should not make any difference at all, and the system should still work just the same as it did before. And we can make sure that is true by running all of the tests. And this is sort of what I mean by making incremental progress while keeping the system running. And you will see me run the tests throughout this video again and again and again. Now that all of the AST nodes are in the AST arena, we can, after passing an expression, iterate the AST arena to print the order in which the nodes are allocated. This shows us that the AST nodes are essentially allocated in source code order. First the 1, then the plus, and finally the 2 in this example. To fix the order, let's talk a little bit about how expression passing works. Let's consider the following two expressions. 1 equals 2 times 3 and 1 equals 2 or 3. Because C operator precedence is weird, these should get evaluated in the opposite way, meaning the first equation has its implicit parentheses on the right hand side, whereas the second equation has its implicit parentheses on the left hand side. The code that does this works as follows. There is an operand and there's a stack of AST nodes. Initially, this operand is set to the 1, and there's nothing on the AST stack. Because there's nothing on the AST stack, we check the next token and see if it's an operator. In this case, it is an operator. It's the equality operator. Therefore, we allocate the corresponding AST node for the equality operator, push it to the AST stack, and restart passing. After restarting, we get the new operand, in this case the 2. But now there's something on the AST stack. Therefore, we compare the operator precedence of the next token with the precedence of the top thing on the AST stack. And here's where the two paths split. Multiplication has a higher precedence than the equality operator, and therefore we first push the multiplication to the AST stack before finishing all of the operations. Whereas for the OR expression, it has a lower precedence than the equality operator. This means we first finish the equality comparison operation and then push the resulting node as an argument to the OR expression, to the AST stack. Here we can also see where the allocation ordering problem happens. We immediately allocate the AST node when we need to put the operator on the stack, before we are passing and therefore allocating the right-hand side of the expression. And therefore, the allocations will come in source code order. To remedy this issue, the solution is to put more information on the AST stack, allowing us to essentially delay when we're allocating the AST node to the part where we are finishing the node. After all that, the allocation order seems to be correct, but there's still a problem. You see, an expression like 1 plus 2 does not really return an AST node for 1, an AST node for 2, and an AST node for the add operation. Rather, does the calculation, constant propagates it, and returns the result. Therefore, when finishing the plus operator, there's a corresponding function, perform integer operation, that is being called. And this function simply overrides one of the AST nodes, namely the AST nodes corresponding to the left-hand side. This is bad because it means that there are now two nodes in the AST arena that the old system was simply able to drop. And so what we need to do here is twofold. First of all, simply do not allocate the AST node corresponding to the plus operator. And secondly, we need to deallocate the node corresponding to the 2. For this, I introduced a new function called pop from AST arena. Because we allocate the AST nodes into an arena, we can only ever deallocate the last thing we have allocated. This function makes sure that the node that is being passed into it and thus being deallocated is the last thing in the AST arena. And this pop from AST arena is now called from perform integer operation. And so the assert I just introduced, that's gonna go off a lot. And this is because a bunch of operators use perform integer operations after pushing the node corresponding to their operator. To fix up this pile of binary expressions, I would run all the tests, pick up an expression from a random test that caused an assert, and then fix it up. Do this again and again, and after all the tests passed, I checked it in. The next big problem I encountered were implicit casts. These get inserted for binary expressions, like for example a plus b, when the two sides of the expression do not have the same type. Here the problem is that we only know whether we have to insert an implicit cast for the left-hand side after we know the type of both of the sides of the expression. But if we were to naively push a cast, that would mean that we would cast the right-hand side of the expression. Because in the new system, unary expressions pop the top thing of the AST stack, perform the operation, and then push the result to the stack again. Here the solution I came up with is to introduce a new node, a AST cast left-hand side. Then instead of operating on the top of the stack, this new AST cast left-hand side will operate on the second entry of the stack. And to make this new node work with the old system, I will for now simply treat it the same as AST cast. But wait, that means that there is currently no functional difference between AST cast and AST cast left-hand side. And that means we could be choosing the wrong one in a bunch of places. That is bad. And so the solution I came up with is to introduce some new checking that checks that when we are iterating in the new way, the operands match the operands that we get when iterating in the old way. So here we were currently dumping all of the nodes. I introduce an AST stack and mutate it to iterate in the new way. A primary expression simply pushes itself to the stack. Unary expressions pop the top entry and then push themselves, except the new AST cast left-hand side, which operates on the second entry. Binary expressions pop the top 2 elements from the stack and then push themselves. And then there are some special nodes, for example function calls, that need some special handling. And we check that the operators that result in this way match the operators that the AST still has from the old system. Compiling a small test program with this additional checking still works. But when we are running the test suite, 71 out of 346 tests fail. And I won't bore you with all of the failure cases, but here's a small rundown. First of all, there was a bug in the check itself. Then a lot of the nodes that were implicitly allocated for casts were too late. Casting constants would push a new literal instead of reusing an old one. Size of and align of expressions are kind of interesting because in the old system where they would simply forget about the expression that they were taking the size of. But now the whole expression is on the AST arena, and so we need to delete the whole expression. And then lastly, certainty references needed to be constant propagated and hence popped off the AST arena. And so on and so forth. Of course, after each of these changes, I would disable the checking code and rerun all of the tests to make sure I didn't accidentally break anything. There's one bigger change I want to talk about before we can move on to later parts of the compilation pipeline. And that bigger change implicates compound initializer lists. What are compound initializer lists, you might ask? Well, when you have a declaration of compound type, so either a struct or a union, you can initialize it by using a curly brace and then a list of initializers and in the end another curly brace and so on. And these initializer lists are quite powerful in C, but they're also quite weird. For example, this monstrosity compiles, where we have these 4 members sort of in the structure. The first member is implicitly initialized to 0 because it was not initialized in the initializer list. The second member is initialized to 1 because it's specifically initialized by name. But then the third member is implicitly initialized because of the current object semantics. And these current object semantics even recursively go into other structures. So this I'm 3 deep is the third thing that is initialized. The way I currently implement these in my compiler is sort of stupid. I'm implicitly building up an AST assignment expression, and I'm pushing a bunch of AST member nodes. But this simply causes me to have to iterate all of these expressions and all of these AST member nodes again to figure out the size and offset of the assignment. And this is happening both in the x64 backend as well as the evaluate static initializer function. I now changed it to keep track of the type and the offset within the left-hand side. And I've introduced a new AST initializer node. In the backend, instead of iterating using a general system to evaluate the assign expression, I now have to iterate all of the initializers in the initializer list and emit a store at the correct offset for the correct type onto the stack. For evaluate static initializer, we can now get rid of a loop that was trying to figure out the offset within the left-hand side. Another problem I encountered were compound assignments. Not compound initializer lists, but compound assignments. These are assignments like, for example, plus equals. And these caused a problem where the left-hand side of the operation was of a weird type. So for example, bool or bit field type. And in these cases, we cannot simply use a machine instruction to perform the operation. And therefore, in the old system, I would transform the AST node into something that would more closely model what the C-spec wants. So I would take the address of the left-hand side, store it in an unnamed declaration, and then reference it both for the left-hand side and for the operation. But I think actually the new system will be able to handle these sort of cases way better, because we can duplicate the left-hand side expression on the stack using a new AST duplicate left-hand side node. But currently we don't have a backend that handles the new way. So for now, I put a hack in there, pushing the nodes onto the other arena So it works with the old system and the new system does not exist yet. And with that, we are down to 5 fails. Fixing up constant propagation for float compare operations, 3 fails. Fixing up array sizes polluting the AST stack, 2 fails. Making sure the choice expression of generic is not evaluated and therefore deleted from the AST arena, 1 fail. Constant propagating an offset of array subscript expression in a very specific case, and we are done. All AST expressions are now allocated in execution order. So we can now get to statements. But remember this, thinking is for nerds. Yeah, I did not really think about this one at all. So we now have the ability to iterate the AST expression nodes in this reverse Polish notation sort of way. And the idea is now to emit code for the nodes in exactly that order. But currently, after one expression, there's simply the next expression, wherever that may be. So at first I thought I would return more information from parse expression, like maybe the start and end of the expression. And then a statement would point to the start of the expression and the end of the expression. But then I thought eventually statements should also be IR. And it seemed like a very large change that I then had to revert. I also thought about inserting some sort of stop point, for example an AST return expression value or something stupid. But then I thought that this stop point could simply be the next statement. And so I moved the AST order checking into parse imperative block to also check statements. And I started allocating some of the statements in the AST arena. But even with that, we still sort of have the same problem. For example, if we have an if statement, then it is currently followed by the code for the then clause, which is immediately followed by the code for the else clause. And there are no nodes in between. But again, thinking is for nerds. So instead of thinking about these problems, I decided, let's just emit some machine code. The main function that currently emits machine code is emit code for AST. And we have to completely rework it. And it is like 2K lines of code. So we have some work ahead of us. Emit code for AST works by taking an AST node, switching on what kind of AST node it is, and in the end returning an emit location that represents the resulting value. There are a couple of types of emit locations, but to understand the system, I think 3 are important. Loaded emit locations represent registers. These would, for example, be returned from a plus operation. Immediate emit locations come from integer literals and represent integers. And register relative emit locations represent L values, so memory locations. Either globals or stack values or dereferenced pointers. For example, for an expression like a plus 1, emit code for AST would first be called on the node corresponding to the plus operation. It would then first recursively call itself on the left-hand side and return a register relative emit location that represents the location for A. So for example, if it's on the stack, maybe RBP minus OX10. Then it would recursively call itself on the 1 and return an emit location immediate that represents this 1. Now because there's no x64 instruction that returns a register and takes both a memory operand and an immediate, that means emit code for AST will need to load the left-hand side into a register first. After loading it into a register, so an emit location loaded, it will then add 1 to that register and return it also to the caller as an emit location loaded. The new system will work very similar, but instead of calling itself recursively, the new function emit code for scope already knows that the AST nodes are sorted in execution order, and therefore it will first see the A, then the 1, and finally the plus. Hence it will first push a register relative emit location for RBP -10. Then it will push an immediate emit location corresponding to the 1. And finally it will encounter the plus. The plus will pop both of these emit locations, load the left-hand side, add 1, and push in the end the emit location loaded just like we did before. And now here's the program I want to make work first. This looks more scary than it is. Most of it is if zeroed out. There really only is a return and everything else are integer literals. Except for some reason I decided to implement a bare bones version of function calls to work with the new system. This is by far the most complicated expression to implement, so I'm not sure what I was thinking, but okay. In this most basic form, I'd simply have to pop all of the emit locations from the emit location stack and then load them in the correct registers for the arguments to the function. And maybe this example isn't the most interesting because it barely produces any code, but the important thing is it compiles and runs. I do though still have to disable debug information because it expects me to fill out some sort of information during code generation. Now for if statements. I have to admit, I was kinda hoping that while programming something would magically hit me and I would just realize how to do it. But instead I realized that this won't really work. First, because we're linearly going through the nodes, we would need some sort of else or end if nodes at the end of the if. There is no other way, I don't think. But second, I also realized that my implementation of the logical and logical or operators is wrong. Because if, for example, the first operator of the logical OR is true, then the second operator shouldn't be executed. But in the way I currently pass and evaluate them, well, both sides of the logical AND operator will first be evaluated, and then the logical AND will be evaluated. And I realize this because there's some special code for logical OR and logical AND conditions for if statements. Well, that means we actually have to do the unthinkable. We actually do have to.
Read.
After doing some research, it seems that there are two popular ways of doing if statements in an immediate representation. The first one and the main one is using basic blocks in a control flow graph. So each basic block is sort of a node in this control flow graph. It contains a couple of instructions, and then in the end, corresponding to the jump instruction, that it has branches to other basic blocks. This seems to be useful when doing optimizations, but I'm currently not going for optimizations, and therefore I want to choose the second version. The second version we can best see when we are looking at the Wikipedia article for the 3-axis code IR again. Here we can see that they use labels and conditional jump instructions. So we introduce an asked label, an asked jump, an asked jump if true, and an asked jump if false. Each label has a label number and each jump knows to which label it is jumping to. In the backend, we already have some code that takes the various statements and emits jump instructions. So this more or less also amounts to moving the code that is already there in the x64 backend and lifting it from the backend to the parser. In the backend itself, we then have a simpler job. We simply allocate a jump list for each label, and during the emit process, we save the location of each of the labels and each of the jumps. And then after we are done with that, we simply iterate all of the saved information to patch up the jumps to jump to the correct locations. For an if statement, we now first have to pass a condition expression, and then we push one of these asked jump if false nodes to jump over the then condition if the condition expression was evaluated to false. At the end of the then condition, and if there is an else branch, we then also have to jump over the else branch. Similarly, here's the new code layout for while statements, and for do while statements, and lastly for for statements. Here the order is somewhat interesting, because the nodes are not evaluated in source code order. In the source code, we first have the initialization, then the condition, then the increment, and then the body. But in the emitted code, we have to have the initializing first, then the condition, then the body, and then the increment. For this reason, during passing, I first skip the source code for the increment, pass the body, and then in the end pass the increment. While this feels somewhat hairy, I could not find any reason why this could be a problem. But if you can think of one, please tell me in the comments. Now I have like at least 10 hours of footage of me porting all of the different expressions from the old function, emit code for AST, to the new function, emit code for scope. And there's also like 3 hours of footage in there from me just rewriting function calls. So there was like a whole lot of work there, but I will spare you the grindy details and only touch on the interesting nodes, starting with switch statements. Passing-wise, a switch statement is a switch followed by a controlling expression, followed by a statement. Usually the statement is a new scope, in which case it can contain AST case statements. These AST case statements are added to a list of case statements which is on the switch itself. So they are both on the switch and in the AST arena, meaning that they will be executed. Same thing is true for the default case. When generating the code for the switch, we sort of just emit an if statement for every case. In the future, we should do something smarter here. So we iterate over the list of cases, compare the controlling expression against the case value, and emit a conditional jump. The jump does not know where it has to jump right now, as the case labels have not yet been emit. They come later in the AST arena. And therefore we stash the jump on the case statement. And when we find the case, we can now simply patch up the jump. But I guess looking at it now, I realize that switch statements actually haven't changed that much between the old system and the new system. I don't know why it took me so long to port them. Anyway, let's look at static declarations. Look at this function. Currently the emitted IR would look something like this, meaning that the IR for the static declaration is also within the same function as the IR for the rest of the function. But this would mean that the result would always be 3, because the initializer of the static variable would be evaluated on every call. This is obviously wrong, and so we sort of have to be able to delete those nodes. But on the other hand, we need those nodes because we have to be able to call evaluate static initializer. So what I came up with is to insert some sort of AST skip node before the initializer of a static variable. And this works fine, but feels somewhat stupid. The next interesting thing I want to look at is intrinsics. For anyone who has seen my implementing alloc-a video, you know that there are barely any intrinsics in my compiler. But alloc-a is one of them. And it broke. First of all, I forgot to keep track of the maximal amount of function arguments to any call, which we needed for alloc-a to be able to allocate the right amount of stack memory or find the right position for the stack memory. But after fixing that, the test still did not work. At this point, both line information and debug information is semi-busted. So debugging any problem is really fun. But I eventually figured out that the condition of this while statement was misbehaving. So let's talk a little bit about conditions and logical expressions. As I already alluded to earlier, the problem here is that we execute both the left-hand side and the right-hand side of logical expressions. Therefore, I tried to change the system to work with the new AST jump if true. The problem here is that what it means to be false depends on the condition. In our example, we have this minus amount and string 1 equals string 2. Comparing a value without a condition implicitly compares it to 0. So that means there's a non-equals operator in the first comparison, but an equals operator in the second comparison. Now this whole expression gives us all of these AST nodes. Here the important part is that the last jump if false should now check for inequality in the first case, but for equality in the last case, which is a problem. In the old system there was a special function for emitting condition expressions called emit code for condition. This function would first specially treat logical OR and logical AND expressions. In the end, letting the while statement decide where all of the successes go and where all the jumps go. To re-implement this behavior, I would now have to somehow move all of this logic into the parsing code. I tried to do this for a while, mapping out how the IR might look, but then I ended up just sort of giving up and just made every conditional expression load their value. So here's the new way of doing things. I emit a jungle of jumps and allocate a temporary memory location that I assign 1 or 0 to. Similarly, here's the code for logical OR expressions. Obviously the emitted code for these are a lot worse than it was before, but the allocate test works again. And pretty soon after, everything passes. Wait, so where are we now? What did we just do? Well, we first of all made sure in the first step that all of the AST nodes are allocated in execution order. And now in the second step, we implemented a backend that can iterate these nodes in exactly that order and emit code in that order. So while the nodes are still called AST nodes, they sort of behave as if they were IR nodes. But this means we should now be able to get rid of the operands of, let's say, an AST binary op. But if we try to do that, we can see that the compiler still complains a lot. And this is because, as I also alluded to in the very beginning, we not only use the AST when generating machine code, but we also iterate it in evaluate static initializer when we are figuring out the value of global declarations. Finally, we also reiterate the abstract syntax tree when we are emitting debug information for scopes, variables, lines, and functions. And this is actually where I want to start, because debugging miscompilations without semi-working debug information is really annoying. First of all, line information. Line information essentially boils down to associating offsets in functions with line numbers, i.e. generating offset line number pairs. In the old system, I would store a byte offset in function on each AST node. Each AST node also had a token associated with it, containing the line and column of the operation. During debug information generation, I would recursively walk down the tree in execution order, and whenever the line changed, emit one of these line offset pairs. In the new system, we don't want to put things willy-nilly on the AST node anymore, or what will be the IR instruction. So we should not use these members. But we have also gained one advantage. We have already sorted the nodes into execution order and put them into a linear buffer. This means we can, during parsing, emit offset line number pairs, where the offset specifies an offset into the IR of the function. And then later, during code generation, fix up this offset to be an offset into the machine code. In the end, during PDB generation, we then simply write out the line number offset pairs we have collected. After that, the line information is still sort of busted, because line information is one of those things that always needs some trial and error to be able to make it usable. But at least it's not buggy anymore, unlike debug symbol information. Debug symbol information worked somewhat similar to debug line information. We recursively iterated down the abstract syntax tree again to figure out what local types there are, what local variables are on the stack, and where do other scopes start and end. To iterate down the abstract syntax tree, we use the fact that each scope currently has a singly linked statement list of all of the statements in the scope. This list was necessary to be able to walk down the syntax tree for code generation. But now that during code generation we don't need that anymore, it has become sort of useless. When we are only interested in producing debug information, we can instead keep a list of all of its subscopes only. Each scope already contains a list of all of the declarations and local types it contains. And these were already used to produce debug information, making this a fairly trivial rewrite. While making sure that everything still works, I noticed that suddenly my tests reported to take a very long time. I mean, a little slowdown might be okay, but like 400,000 years for a simple test file does seem a little bit excessive. And so there's some sort of bug here. And this is the type of bug where you immediately get annoyed. It's a floating point number that is used as the argument to a var-args procedure. And it's been probably broken for a while. So here's me looking into the var-args floating point code. And then looking into the code that is actually generated for such a call. Figuring out that the incoming value was already wrong. And looking into OS_getTime in seconds. This function divides the performance counter by the performance frequency. But look at that. That's not a divide instruction. So yeah, apparently I don't have any test cases that test that dividing floating point numbers works correctly. And what was happening is that instead of dividing the two numbers, I was multiplying them, making a big number. Anyway, where were we? Right, removing the operands to AST binary op. There are some random places doing parsing where the operands are used, but the main culprit is this evaluate static initializer. What does it mean to evaluate static initializer? Well, for simple declarations, we figure out what bytes make up the declaration. These bytes may be constant, but they also may be a pointer to some other declaration, plus potentially some offset. In this more complicated case, we have to figure out the offset bytes and emit a patch, which we have to fill out later on when we know where all of the declarations are located within the executable. For more complex types like structures, instead of just being a single initializer, we have to evaluate a sequence of initializers. In the code, this works as follows. Each initialized declaration has an assign expression. This expression is either an AST assignment in the simple case or an AST compound literal in the more complicated case where you have a structure. A compound literal is more or less a list of AST initializers, each corresponding to one assignment. For simple assignments, we create a temporary AST initializer node and push it to the list. Then we call evaluate static initializer internal. This function iterates down the tree until it either finds an address of operator or a plus or minus operator. If it finds an address of operator, it tries to evaluate the rest of the expression as an L value. So for example, a global declaration or a string literal or something like that. Plus potentially an offset, for example, from a member expression. For a plus or minus operator, it does the same thing, but both with the left and the right hand side. And then tries to figure out if we can add the two sides at compile time. As you can see, this function is already non-recursive, except for the case where you initialize with another struct literal. But we still have to introduce an AST stack to handle evaluating the left-hand side and the right-hand side of a plus or minus operator separately. The biggest difference here is the order in which we see the nodes in. In the old way, we would iterate down the tree to evaluate the offset within the right-hand side, and then we could write the value as soon as we saw a constant. In the new way, we see the constant first. Then we see all the nodes that give us the offset within the right-hand side, and finally we see the AST initializer in the very end. And only once we see the AST initializer, we can write the value in. After that works, the last hurdle to remove the operands from the AST binary op is during code generation. Here, for example, in the comparison cases, I need to know the type of the operands. I cannot infer the type of the operands from the return type, as the return type for comparison operations is always int. Because of how the system works, I actually know the size of all emit locations. But I don't know whether they are floats, or whether they are signed, or whether they are unsigned values. Therefore, I came up with the idea to introduce float and signed variants of the comparison operations. And then just before pushing one of these operations to the AST arena, alter its type to convey the information to the backend. And with that, binary expressions compile without operands. Next, unary operators. And the only really hard one here was a cast expression. And I simply punted by making it a special node that has an operand expression. Now most operations do not have arguments anymore. They simply consist of just the base AST node. Well, what does that mean? Well, it means that the compiler is now essentially working with an IR. While the instructions are still called AST nodes, they do not form a tree anymore, so are definitely not an AST anymore. So are we done? Well, sort of, but the whole idea was to remove the amount of memory needed for the AST as much as possible, and the AST node is still quite fat. Of the remaining members, the easiest to remove is probably the token. The token is only used for error reporting and therefore should not be used anymore after parsing. One of the techniques I like to use for cases like this, where you want to remove one member of a struct, is to introduce a define like remove token from struct. This allows you to patch up a piece of code and then easily toggle between the two versions. Toggling to remove the token and then compiling will highlight all the locations where the member is used. This means I can easily search through them to find like a leave function where the token is only used in an error report, like for example this push cast function, and then introduce a new token argument to the function that replaces the previous usage of the member. Now toggling back the define to not remove the token again and compiling will only highlight all of the calls to the push cast function. And after fixing all of the call sites, we can easily rerun all the tests to make sure I did not break anything. Rinse and repeat for like 3 hours and we have eliminated the token. Though in this case I sort of ended up regretting attacking it in this way, because when I tried to do the same thing for the type, it ended up not really working that well. This is because whereas the token is sort of an input parameter to all of these routines, the type is something that in some way is returned. In some cases literally, for example for integer literals where we infer which defined type to use, but also more indirectly, for example for maybe insert arithmetic conversion casts, where it figures out which type both the left-hand side and the right-hand side should be casted to. The easiest solution I could come up with is to essentially introduce the same struct as AST. But instead of living on the AST arena, it will live on the stack of the pass expression function. And it will point to the operation on the AST arena. But this new expr struct or expression structure might as well also include the token again. And it is essentially used the same way doing expression passing as we used the AST nodes before. Meaning I did not gain that much by eliminating the token from the AST. After introducing this expr and keeping it up to date inside the pass expression function, I used the previously mentioned technique again. Toggling to remove the type, identifying a relatively isolated place where the type is used, fixing it up, untoggling the define, and then running all of the tests to ensure I didn't break anything. And this worked very well for the parsing code until I hit code generation. Here the problem is that we've actually lost the information, and the information is needed for some of the nodes. For example, the code generation for the AST cast looks at both of the source type and the target type to figure out what kind of instructions to emit. The stupid solution here is to simply give all of the instructions that need the type explicitly. And I did that at least at first for both AST cast and later also for integer and float literals. But then I remembered that we already solved this problem once before when we introduced the float and signed variants of comparison operations. Here we had the problem that because we removed the operands from the AST node, we could therefore not get the type for the operation from them anymore. And in a sense, here I already introduced some nodes that were purely IR nodes that never actually served any function in the abstract syntax tree. And really, this is how the whole system should work. Once you write out a node into the AST arena, or soon to be called IR arena, it should be an IR node and should have an IR kind. But the AST kind still has to exist because we need it doing expression passing. So let's do what I do best. Dream up an IR from looking at exactly the operation performed by the backend, and then slowly build up a parallel system by porting over all instructions from emitting AST instructions to emitting IR versions of the instructions that include the type in their IR kind. And we start off by doing it for the comparison operation, as we've already started on them. I made every operation be very explicit about its type. This is currently not really necessary because the backend keeps track of the size of the values. Maybe I revise that decision in the future, I'm not sure. For comparison operators, the new IR instruction kinds now encode their operand types using some math. That took me an embarrassingly long time to get right. And then the backend reverses that math to decode the operand types again. Afterwards, it can more or less use the same code that it did before. Similarly, here are increments and decrements. These use the new IR type I introduced to represent basic types. A lot of the more complicated nodes like load address, deref, subscript, and so on translate more or less one-to-one. We don't have to change anything. But yeah, this was mostly just another 17 hours of relatively mindless grinding. But I needed to get to 10k lines of code edit in the end anyway for the thumbnail, so it's all good. After all is said and done, we should not really be using the AST struct anymore. And in effect, after cleaning up some residual usages, we don't. And this means yes, finally, the refactor is done. We are done. The end. Except I only ever made sure that the test suite still works. The real test is to see whether the real-world projects like curl or SDL still compile. This wasn't actually too bad. I did most of it in like a 5-hour sesh, but here's a little rundown of the bugs I encountered. Firstly, freaking CMake is not backwards compatible? Like, how is that allowed for a build tool? But okay, I was able to download an older version that I was using before to do all the testing. Anyway, glfw caused an assert inside the compiler because the compiler had a special code path for adding 0 doing pointer arithmetic, where it simply would delete the 0. But this caused an issue for like adding 0 to an array, because here first there would be a cast inserted to cast the array to a pointer, and this was a left-hand side cast. But then if we eliminate the 0, that means it casted the wrong value. In a similar vein, assert false broke. The implementation of assert false is with a logical OR and a comma expression. The compiler here tried to constant propagate the left-hand side of the OR with the 0 of the comma expression. But here the left-hand side of the comma expression was in the way, so an assert was fired. I solved this by simply not returning an integer literal from a comma expression, but returning a knob or something, simply to keep the system from trying to constant propagate a comma expression. libpng caused a bunch of problems where the code was compiling, but then was misbehaving when I was running the libpng test suite. These sort of issues always take a while because I am unfamiliar with the code I am debugging. But one problem was that I forgot to load bit fields when they were operands of logical OR or logical AND expressions. And this was causing some if expressions to misfire. And another crash bug was that I did not spill all of the volatile registers to the stack before every conditional jump instruction. NeoVim caused a compiler assert because the back-end casting code expected to never encounter an integer literal because of constant propagation. But because comma expressions do not return integer literals in the parser, but they do during code execution, this can now happen. SDL caused a problem with line information if the last statement in a function scope did not emit any IR instructions. And finally, SDL3 showed that incrementing floating point variables did not work anymore. But after all that, here's the real question. Do we actually get anything? Do we compile faster now? Well, this is the repository for the V compiler that is already pre-processed into a single C file. And this is the target where I was noticing that parser push ask took a good amount of time. Prior to the refactor, it took like 2.2-ish seconds to compile and like 1.2-ish seconds if the compiler was compiled with optimizations. After the refactor, we are done to 1.9 and just under 1 respectively. So I think that's a pretty respectable improvement, and it also shows that memory pressure was probably the problem, because both the debug and release version sort of lost the same amount of time. For reference, the fastest C compiler, the tiny C compiler, takes around 0.7 seconds. But it sort of cheats because they ship their own incomplete version of Windows.h, and therefore they only pre-process like half as many lines. So I think that's very good and very respectable speed up. And I thank you all for watching. And I have some other video ideas in the making. I would like to eventually port my compiler to Linux and maybe try to compile the Linux kernel. That would be fun. But that's maybe a little bit further in the future. I want to kind of make like a Godbolt thing and work on like the quality of code that I generate, because I think currently it's utter garbage. I want to retry to attack the preprocessor, because that's currently where all the time is spent when compiling. And lastly, I think the next thing I probably want to do is to work on a table-driven inline assembler, because inline assembly is one of those things that's like doesn't really work right now. It just works for the intrinsics. Anyway, if you have another idea what I could maybe do, or if you liked the video, like do all the YouTube things, I don't know, man. Anyway, thanks for watching. Goodbye.